Selecting k objects from n options. This is something that we've seen now several times in previous videos, but here I just want to not give any new results, not any new formulas, but kind of just see all the different ways all at once, because I think it helps to put them all in a chart and kind of summarize a lot of what we've already said. So the easiest case of this is the top left, where order matters and repeats are allowed. If you have this, this follows from fundamental principle of counting, because we're selecting k objects from n options. So I have n options for the first collection times n options for the second times and so on, n options for the last selection. And how many of these? I'm selecting k objects, each with n options, right? So I get n to the k. So this is selecting k objects from n options where repeats are allowed and order matters. A great example of this is setting a pin, right? Where you're allowed to use the digits 0 through 9, 4 digits. 10 to the fourth is how many pins you can choose, right? Now from here, the next easiest formula to go to is from this one. Use the same approach, but come down here, right, to get permutations. Now order matters, but repeats are not allowed. And what is this formula? It's very similar. You're picking k objects, but since repeats are not allowed, every time you pick one, you lose one option, right? So that's why it's descending. Instead of it just being n times n over and over again, it's n times n minus 1 times n minus 2, and so on down to n minus k plus 1, right? This is our formula for permutations, right? For n permute k. Well, and you can also write this as a factorial, right? N factorial over n minus k factorial. Either of those works just fine. So this is our the permutations formula. Now think back to how can you get the combinations formula from the permutations formula? Well, you just divide by k factorial, right? So once order does not matter, whence Shakespeare presents combinatorics, whence order does not matter. I won't even try to fake a old English accent. But so when order does not matter, we now are doing n choose k instead of n permute k, right? So this is, you can do n choose k. How do we get this? You do exactly the same formula as before, right? But now you're going to divide off by the k factorial ways to rearrange those k objects that you've selected, right? And this becomes the binomial coefficient, which is n factorial. You could just leave it as the formula I have written up above, but it's also very common to write it like this: n factorial over n minus k factorial times k factorial. They're both very, very common. All right, then we have fundamental principle of counting, right? Giving us n times n times n times n to the k. That formula just adjusted ever so slightly to get repeats not allowed by subtracting one from each of the options as you go, right? Then that formula you could divide by k factorial to get n choose k from n permute k. The last thing we did was here. We went this way in the table, right? We used our choose without repeats formula to build a choose with repeats formula, right? And this is our n plus k minus 1 choose k, right? This is the formula, the stars and bars construction, right? And I won't go into that. That's a big complicated process, right? But so this is stars and bars, right? That's our that's how we get that last formula, right? That where we say that a selection of k objects from n options where repeats are allowed and order does not matter. What does that correspond to? It corresponds to the selection of k. We want to pick k stars. Oops, down here. So we down here. Here we go. So pick k stars from what? From, you want n minus 1 blanks for the dividers between your options, right? Which are the bars, plus the k star. right? So you have n minus 1 plus k is how many blanks you have, and you're selecting k of those to become stars versus, and then the rest are bars by default, right? So there we have all of our all 4 of these counting formulas from the previous 4 videos. Right? But I think it's helpful just seeing them all in one place, seeing all the formulas all at once and how they relate to each other. To be honest, maybe is a little difficult to memorize these as separate formulas, but thinking of this table and how each formula flows from the previous, I think is a really good way to package all of this information and working examples, of course, right? So that's what I want to do next is let's work a few examples that show where we don't know upfront which of these formulas we're going to need, and we can talk through a little bit through the reasoning process of how do you pick this? How do you decide which formula to use in which context? So let's do this. Let's say, what is the probability of, let's say, winning the lottery, where let's say the lottery is this particular lottery is given by, you have to choose correctly 5 numbers out of 50. Right, so you have your little ticket that you buy, and when you buy your ticket, this is how this particular lottery works. So we have our ticket, and then you could bubble in your 5 favorite numbers. There's 1, 2, 3, 4, 5, 6, 7, 8, right? There's all these numbers printed on this card, all the way down to, right, to 49, 50. So this is our little card. And then, if I want to play the lottery today, I'm gonna say, okay, today my lucky numbers are 2, 6, 8, 49, and 50, say, for example, right? So, so I could play that, right? I could play 2, 6, 8, 49, 50, for example. That might be my selection of 5 numbers out of 50, right? I'm going to bubble those in. And if I match all 5 numbers, then I win the lottery. And here we won't worry about secondary prizes of, you matched 3 out of 5, you matched 4 out of 5. We won't worry about that. Here we'll do the simpler scenario of just, do I win the jackpot? Do I hit all 5 or not? Right? So here, all we have to do is say, okay, on one ticket, I played my favorite option, right? So there's, my one ticket, maybe my selection was 2, 6, 8, 49, 50, for example. And then what I want to think about is what are the total number of possibilities? Right, I have my one ticket that I actually bought out of the total number of possibilities. Well, what would that total number of possibilities be given by? It's the number of ways that you could possibly select 5 right numbers from, which this is our k, right? K equals 5 numbers from n equals 50 options, because it's the numbers 1 through 50 are the options. Now, here's what I really need to think about. Does order matter? And are repeats allowed, right? So I would claim that order does not matter in this case, because think of the person who you hand the ticket to, right? You bubble in the numbers, then you hand it to them at the convenience mart, right? They have no idea whether I bubbled my numbers 50, then 49, then 6, then 2, then 8, right? If I did that, or if I did, 6, then 8, then 2, then 50, then 49, they have no idea. They can only see what numbers have been bubbled, not what order they were bubbled in, right? So order does not matter. Also, repeats are not allowed. Why not? Well, maybe in a different game, maybe in a different lottery they are, but in this style lottery, you're not allowed to only, I'm not allowed to pick just 4 numbers and say, I'm going to do 2, 6, 8, but then I'm going to double bubble 49 instead of bubbling a fifth number, right? That's not a valid way to fill out the ticket. You have to pick 5 distinct numbers, right? So repeats are not allowed. You can't just do a double thick bubble or something on one of your numbers, right? So repeats in this case are not allowed. So what does that give me? That means in the little table, where am I? Order does not matter. Repeats are not allowed. So I'm here, right? I'm using the n choose k formula. So that's what I want to do here. I want to say, okay, then this probability is actually 1 over n choose k. And so what does that become? Well, and I even know my n and k, right? It's 50 choose 5. And you can write it that way, or you can write it, again, this notation is very common, 50 choose 5, right? With the binomial coefficient notation. Now I can write this out, right? So this is, what is this going to be here? It's going to be 50 times 49 times 48 times 47 times 46, right? Do 5 numbers divided by 5 factorial. 5 times 4 times 3 times 2 times 1. So that's how we evaluate that binomial coefficient, right? Then, a little more clear. There we go. That whole thing is a denominator, right? Then I can just calculate that as a number, and there we go. There's my probability. If I calculate that, if you do all the arithmetic on that bottom number, we get 2,118,760. There's 2,118,760. So that's the lot. That's the odds on this lottery. It's about 1 in 2 million, right? Which is, for lottery standards, is actually pretty high odds compared to most lotteries that are actually out there, right? 5 out of 50 is usually not as bad as what you're actually trying to hit in most lotteries these days. And of course, this you can work out as a decimal if you wanted to express your probability as a percent, which is a very common way to express probabilities, right? So that if you do that as a decimal, it's 4.7 times 10 to the negative 7. So if you want, you could say then that's 4.7 times 10 to the negative 5th percent. And this is approximate, of course, right? It keeps going. And then this is, so now we can move the decimal 5 times, right? So we'd say, okay, it's 1, 2, 3, 4, and then the numbers percent. There we go. So there's this minuscule probability of winning the lottery, right? Of winning this particular lottery. Okay. So there's an example where we used n choose k, right? Up front we didn't really know what counting formulas we were going to use in this scenario, but that was how we ended up lining this up with the right tile in the table, right, and figuring out what is n, what is k, and applying the formula. So, all right, so there we go. There's a lottery example. Let's look at another one. Let's look at another example. Let's say that me and my wife and my son are going to let's say a burger eating challenge. This is the kind of thing we would do. And let's say this particular burger eating challenge is not a eat the massive burger, but eat a quantity of burgers, right? So they're all regular sized burgers, but there are lots of them, right? And let's say this particular challenge is for 3 people to eat 10 burgers, right? So, but you just have to have your 3 people collectively eat the 10 burgers. It doesn't matter who eats how many, right? So you don't have to have a even distribution of at all, right? Maybe one of you is just not hungry at all that day and doesn't eat any, and that's perfectly fine, right? So so this is a combinatorics problem, right? How many ways can you distribute the eating, right? So in how many ways can you accomplish this? right? So we have these 10 identical burgers, right? We can't tell them apart. And we want to think about the different ways that we could accomplish this task. So as always, it's always a good idea to just list out some possibilities. Just get a sense for what is going on. If it does, if it doesn't immediately come to you, right? Just do some listing out. In combinatorics problems, it's nice about combinatorics. The answer is always finite integer, right? Finite natural number. It's something that, maybe it's an insanely large finite number, but it's something you can at least start listing and try to analyze the problem that way. So let's think about this. What could I have? I could have 10 here, 0 here, and 0 here, for example, right? There's a extreme case where I eat all 10. Faith and Rocco don't have any, right? They just really weren't hungry that day, but I was ready to pick up all the slack, right? You can think about, okay, maybe 9, 1, and 0. Maybe 9, 0, and 1, right? Maybe 8, 2, and 0. Maybe 8, 0, and 2. Maybe 8, 1, and 1, right? And so on. So this is these are just listing out some distributions, right? And here I'm kind of listing them based on the top number, like what's the largest, well, at least at least for on my side, what's the largest number in my column, right? So so this batch might end up with something like 433, right? Is by this scheme. And again, I'm not being super formal here about and super systematic about how I'm listing these out. But then you could also have it where the largest number appears somewhere else, right? So you could do, say 0, 0, 10, and 0, right? Or, again, just sort of skipping. I'm not doing anything really systematic. We could do 2, 3, and 5, right? Our 3-year-old was super hungry that day. That out ate Mama and Dada. So these are all different ways that we could do this. Well, now think about, and this is why I mentioned it's really good to know not just these formulas, but the constructions behind these formulas, how these formulas come about. It helps a lot knowing which formula when, how to determine which formula to apply when, if you have some sense of where they came from, right? Because what does this remind you of? Well, hopefully it reminds you a little bit of the stars and bars construction, right? Think about this first one. This could be 10 stars, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then a bar and a bar, right? So here, the stars would always start with Ken burger, right? So a star means give Ken another burger, give Ken another burger, give Ken another burger, until you see a bar, at which point we switch and we start giving Faith burgers, right? Until you see another bar, and then you start giving Rocco burgers, right? So, that would be for Ken, Faith, and Rocco, right? 0 for Faith, 0 for Rocco, and 10 for Ken. Just to skip and do a few that are a little more different, right? So that would be this one. Say this one, right? This would be 1, 2, 3, 4, 5, 6, 7, 8 for me. Faith was not hungry that day, so skip Faith and move on to Rocco, who then ate 2, 1, 2, right? Come down here, right? What is this? This is 1, 2, 3, 4 for Ken before we move on to Faith, who ate 1, 2, 1, 2, 3, and then we move on to Rocco, who ate 1, 2, 3, right? So that's what these look like. So these distributions of burgers, so Ken, Faith, and Rocco, this is just another way of seeing the stars and bars setup, right? And we actually know how to do that, right? What is this? This is this list. If we count this list, what are we doing? We're selecting 10 stars from 12 slots, right? And then the other two become bars by default. Right. Now, this is a little bit weird to actually evaluate, right? Or not weird, but cumbersome, right? Because I'm selecting 10 stars from 12 slots. So if you follow the formula, it's 12, 11, 10, 9, 8, right? I have to do 10 numbers up here. 7, 6, 5, 4, 3, right? Is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There it goes, 10 numbers. And then here I have to put 10 factorial. And now, of course, you don't have to actually multiply this out. Lots of cancellation will happen, right? But it's still sort of annoying to even set that up. So there's a trick that is often useful in these cases, which is to say, you know what, instead of picking the stars, pick the bars instead. Just pick the 2 bars out of 10 slots, out of 12 slots, and then the rest are stars by default, instead of picking the 10 stars out of the 12 slots. So it's a nice little trick, because now this is way more clear, or not clear, it's just as clear either way, but the way more convenient, right? So this is 12 times 11 over 2. This becomes 66, right? So there are 66 ways that we can tackle the burger challenge, right? 66 ways to distribute the work between three of us, right? So this is our stars and bars construction, right? So this was sort of the top right corner, instead of the we had the bottom right in the previous, right? Now, one thing that I should mention here is this 3 and this 10. Where is this coming in, right? This, notice, this is, right, it's 10 plus 3 minus 1 over, or sorry, choose 10, right? So this is really just that top right corner, the stars and bars, right, where K was 10 and N was 3, right? So the N equals 3 options, right? And K equals 10, which it might seem a little counterintuitive, because here you're, what are the 3 options? The 3 options are Ken, Faith, and Rocco, right? The things you're selecting are actually the burgers, right? The K equals 10 burgers, which maybe sounds weird, because physically you maybe want to think of like people grabbing burgers. It's like a person is selecting a burger, right? But this is the, I don't know, maybe this is the American Diner version of Wand chooses the wizard or something like that, right? The burger chooses the competitive eater. In this case, you really do want the mindset to be that we're distributing the burgers to the people, right? So the options are, you're kind of saying, I have these 10 burgers, and then each burger, for each burger I can choose one of 3 people to eat that burger, right? And I can make repeat selections, right? Because multiple burgers will be probably assigned to the same person, and in fact have to be by pigeonhole, right? 10 is bigger than 3. And so multiple burgers can be assigned to the same person, and also it's not important what order they're selected in what order you assign the burgers to the people. So so this, it really is the right way to set it up. N equals 3 options, K equals 10 is what's being selected from those 3 options. So it's also why it's very nice to list it out like this, because sometimes it's a little abstract, a little tricky to just pick the N and pick the K. So listing out at least a few of them will clue you in that you're using the right tile, using the right formula. So, all right, there we go. There is just 2 examples, and showing all our counting formulas all in one place. So this is the key table of very key table of combinatorics. This is the essentials kit, the first thing every combinatorialist wants to have at the front of their mind when tackling a counting problem. So, great, thank you.